This next result is the first result that uses the multidimensionality here in an essential way. This is the first result in section 6.5 that isn't just a result in section 6.2 patched together into a multidimensional result. And this is the chain rule. And here is the setup. We're going to start out with 3 domains, or 3 sets. U is going to be a subset of RP, might be a proper subset, might not be. V is going to be a subset of RQ, and W is going to be a subset of RD. P, Q, and D are 3 positive integers. They might be the same, they might be different. And we're going to let F be a function whose domain is U and whose range, it goes from U to RQ, but as it happens, the image is contained in V. G is a function from V to W. And we're going to let H be G composed with F. So the chain rule, remember, is all about differentiating compositions. So we'll let C in U be a limit point. And we're going to suppose that F is differentiable at C. That F of C, notice F of C has to be in V by assumption, and that F maps into V, but we'll assume it is also a limit point. And that G is differentiable at the point F of C. The conclusion then is that H is differentiable at C. And I can tell you give you a formula for DH. DH of C, remember this is a linear operator. It's the linear operator DG of F of C. That's a linear operator from RQ to RD, composed with the linear operator dF of C, remember, that is a linear operator from RP to RQ. And here is the proof. First off, I'm going to draw you a picture of what is happening. So just to keep oriented, here is our region U contained in RP. And we have our point C in the middle there somewhere. And then we've got our region V in RQ. And we've got the point F of C here somewhere. And then finally, we've got our region W contained in RD, and somewhere in the middle we've got G of F of C, also known as H of C, somewhere in there. And we have our functions F going from U to V, and our function G going from V to W. This picture, by the way, is why I bothered with the set W. If you write it out analytically, you might as well just let VG be a function with domain all of RD, but this picture is a lot clearer if W can just be a blob instead of trying to draw Euclidean space. We're going to grab another point somewhere in here, another point X in U, which maps to a point f of x somewhere in V, which maps to a point h of x somewhere in W. So now let's write down some facts. Let's write down some facts using the fact that G and F are differentiable. So if x is in U and x is, then we can write h of x, that's G of f of x. Now, because G is differentiable at f of c, that's going to be G of f of c, and then we add to that dg of f of c, evaluated at the vector, whatever it is we're putting inside the G, that's f of x minus f of c. And then we add to that the norm of f of x minus f of c. And then times some big G of f of x, where big G of f of c is 0, big G is continuous at f of c. Now let's write this out again using the fact that f is differentiable at c. This G of f of c, let's turn that back into h of c. And then we've got dg of f of c. That's our linear operator. And then what have we got here in the middle? F of x minus f of c. That's df of c at the vector x minus c. And then you add to that norm of x minus c times some big F of x. And then we've still got our f of x minus f of c. That's the norm of df of c evaluated at x minus c. And then the norm of x minus c, big F of x. Then there's a big G of f of x. And where big F, of course, f of c is 0, big F is continuous at c. So now let's summarize this again. There's h of x equals h of c. And then next we've got our dg of f of c. That's a linear operator composed with another linear operator, df of c. And that's evaluated at x minus c. And remember, the composition of two linear operators is linear. So this piece here, that's a linear operator of x minus c. So this looks an awful lot like what shows up in the definition of derivative. We just need to figure out how to deal with all these other pieces, this bit and this bit. So where do those go? We can break those up. We're going to pull a norm of x minus c out. Remember, dg of f of c is a linear operator, so we can break it up over the plus sign. And we can pull the constant norm of x minus c. It's a function, but it's also a scalar valued function. We can pull the scalar out of the linear operator. And then, so what we've got is dg of f of c. And then you plug in f of x, because f goes from u to rq, big F of x also goes from u to rq. And then we have another piece. That other piece is we've got the norm of big F of x plus df of c. This is a linear operator, so I can put the scalar x minus c. I can divide by the norm of x minus c. And then we've got our big G of f of x hanging out front. Now let's let big H of x be all this leftover junk. Our dg of f of c evaluated at f of x, I'm going to write that as dg of f of c, the function composed with the function capital F, and then all that evaluated at x. And then we have to add to that big G composed with f of x. I'm writing all these as compositions because I want to use our proposition that says that compositions are continuous, multiplied by the norm of f of x plus df of c of x minus c. And why don't I put the 1 over the norm out there? And now, so we've got that h of x is h of c plus a linear operator composition of two linear operators we have seen is linear. And then the norm of x minus c times big H of x. So it suffices to prove this looks an awful lot like the definition of differentiability. All we need to prove is that our big H satisfies the conditions for a remainder term. Big H of c is 0 and big H is continuous at c. Actually, we have to clean this up a little bit. Notice that we divide by the norm of x minus c at some point. So we'll put a 0 if x is equal to c. And then our whole complicated mess, that's only true if x is not equal to c. But it is true for all x in our domain U, except for x equals c. So let's see what's going on. So first off, we've got that this thing, dg of f of c, is linear. So as we saw at the end of the last video, so it is continuous everywhere. And that is a proposition we saw in lecture 6.5.1, 6.5, lecture 1, part 3. So if you compose this linear thing, it is continuous at c. That's because big F by assumption is continuous at c. And if you compose two continuous functions, then you get something continuous that is by proposition from section 5.4. And f of c is 0, so it's a straightforward linear algebra argument that any linear operator, if you plug 0 in, you get 0. So this first piece of our big H, this thing, it equals 0 when you plug in x equals c and is continuous there. So that piece we're done with. And then this piece we can deal with pretty similarly. G composed. So first off, f is continuous at c because we've seen that differentiable functions are always continuous. This is specifically theorem 6.5.7a. So G composed with f is continuous at c. That is same proposition in 5.4.4 again. And also G of f of c by assumption that is. So we're left with the horrible thing in the norm. So norm of f of x plus the rest of it, df of c of our quotient x minus c over the norm of x minus c. By the triangle inequality, we've got f of x and then df of c of x minus c. But then notice that this vector x minus c over the norm of x minus c, that's a unit vector. So this so the second piece, we've got our f of x floating around. We've just got our norm of our df of c. Because df of c is a linear operator, so by the proposition from the end of last lecture, this is finite. It's not 0. This piece isn't going to go to 0, but it is finite. Now, we also have that f of c is 0. F is continuous at c. So there is a delta greater than 0 such that if x is in our domain U, and also the distance from x to c, which we recall is the norm of x minus c, is less than delta, then the distance from f of x to 0, that's the norm of f of x. Norm of f of x minus 0 is the norm of f of x is less than whatever your favorite epsilon is. Let's say it's 7. So the conclusion is that if x is in the ball centered at c of radius delta, also in U, and is not c, then this thing, the horrible thing in the norm, that is less than or equal to 7 plus the norm of df of c, whatever finite number that happens to be. Now, what we are going to have to use is an exercise from section 5.4, which I didn't assign, but seems to be exactly what we need here. So this is exercise 5.4.2. So this is a chapter 5 exercise, so it's of course in metric space language. Let's let XD be a metric space. F is a function from X to, I think in this case we need it to be RD. G, C is a point in X. We're going to have delta be a positive number, and G is a function also from X, but now mapping into the real numbers. And then if we have that G of X is less than or equal to M for all X in the ball centered at C of radius delta. If F of C is 0, that is the 0 vector in RD. And if F is continuous at C, then FG, that's also a function from X to RD, is also continuous at C. So the idea here is it's well known that if you multiply by two continuous functions, you get a continuous function. But if one of your continuous functions happens to be 0 at your target point, your other one doesn't have to be continuous. It's enough if it's bounded. So by this exercise, which we'll leave it as an exercise, so by exercise 5.4.2 and proposition 5.4.5, which says you can add continuous functions, we have that capital H is continuous at C. And since H of C is 0, that completes the proof. Now we are going to discuss critical points in local extrema. This is a definition that your book puts in section 6.2 for some reason. I think it makes more sense to leave it until section 6.6, where they go into local extrema in much more detail. And also, I didn't really have time for this in the section 6.2 videos. So now we're going to start in on local extrema. We're going to put in a couple of definitions and theorems from section 6.2, and then we'll move on to section 6.6. So let's let X be an open subset of RP. F is a function defined on F. It has to map into the real numbers because a function from X to RP, doesn't have biggest elements and smallest elements. The real numbers are really where you want to be if you want to talk about biggest and smallest. And let's let C be a point in X. All right. So this is actually several definitions. If F is differentiable at C in our weird linear operator sense, and our linear operator df of C is equal to 0, and that is to say df of C of V is 0 for all V in RP. We say that C is a critical point for F. Next definition is that if there is a R greater than 0 such that f of C is greater than or equal to f of X for all X in the ball centered at C of radius R, and because big X is open, we can insist that this ball has to be contained in X in our domain. So f of X is defined everywhere in this ball, then F has a local maximum at C. And definition of local minimum is exactly the same. If there's a positive radius such that f of C is less than f of X, then F has a local minimum at C. So far, this is very much like the case in one dimension, and we'll end up, and the next theorem, theorem 6.2.20, is going to look an awful lot like the one-dimensional theorem. But there's one other definition that we have to write down that shows up in the two or more dimensional case. So here's how this works. Suppose there are two non-zero vectors v and w such that the function f sub v of t, that's f of C plus tv, has a local maximum at t equals 0, and the other one has a local minimum Then we say F has a saddle point. I have tried and failed to draw what a saddle point looks like, but I have a physical model of one in my office, so remind me to bring this to class next time. So what do we expect to be true at a critical point? So let's recall what happens in one dimension. So in one dimension, you can restrict your domain to an open interval. And then the conclusion is that if f prime of C exists and f has a local extremum, sometimes it's useful to be able to talk about local maxima and local minima at the same time. So if f has either a local maximum or a local minimum, at C, we say f has a local extremum at C. So if x prime of C exists and f has a local extremum at C, you aren't guaranteed a derivative, but if you have a derivative, then you all know what it is. F prime of C has to be 0. So we have a not very surprising theorem. We have that if X is a subset of Rp, X is open, C is a point in X, F is a function from X to the real numbers, F has a local extremum at C, and the gradient of F, that is all the partial derivatives of F, exists. And remember that this is a weaker condition than being differentiable in our linear operator sense. Then the gradient of F at C is equal to 0, is the 0 vector. And we remark by theorem 6.2.12b, if the full derivative, not just the partial derivatives, exists, then theorem 6.2.12b says that if the full derivative exists, then the gradient exists, and the full derivative is the inner product with the gradient. So if you know the gradient is 0, you must have that your df of C is also 0. And this is, the proof is pretty straightforward. Let fk of t be f of C plus t times ek. You remember from section 5.3 that we can always put a little ball centered at C inside X, then Fk is defined on the interval from minus R to R. And then partial kf of C is Fk prime of 0, but Fk has a local extremum at 0, and by assumption partial kf of C exists, so Fk prime of 0 exists. So by theorem, the theorem we mentioned above, Fk prime of 0 is 0, so partial kf of C equals 0 for all k between 1 and p. In the next video, we are going to cover, we are going to talk about the analog to the second derivative test. And you may remember that if you're at a critical point and your second derivative is positive, you're a local minimum. If your second derivative is negative, you're a local maximum. And we are going to talk about an analog to that in higher dimensions. It's going to be more complicated. So your homework for today is going to be essentially working through all the linear algebra preamble that you're going to need, that we're going to need for the analog to the second derivative test. So right now I'm going to wrap up this video by writing down two definitions. These are the definitions of the concepts from linear algebra that you're going to be using on your homework. I've tried to keep the linear algebra to a minimum because I'm not sure exactly how much linear algebra you remember, but we are going to need some of it. So here are the two definitions that you're going to need for your homework, which will set us up for the next lecture, the next video for the second derivative test. So let's let U1, U2 up through UN. That's a set of vectors in RP. This definition is more general, but we'll only need it for finitely many vectors. Then the set U1, U2 up through UN. Perp, if we put a superscript with some right angles up there, that's the set of all x in RP, such that the inner product of x with uk is 0 for all of the k's between 1 and n. One more definition. Let's let A be a function from RP to itself. And then if A is linear, and we have the following equation. The inner product of x with ay is always the same as the inner product of ax with y. For all x, y in RP, we say that a is, the term for that is Hermetian, or self-adjoint.